Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with your midterm exam review. So make sure that you understand what all the important terms are. So as we go, if you think back through the course and all the videos you've watched, every one of these quantities is defined a very certain way. Velocity, energy, potential energy, and whatnot. And hopefully you know what those are. In this particular problem, you're just asked to match the stuff on the left with the sentences on the right. That's just that should be as simple as just knowing, for example, that velocity is the rate that your position changes, and which one over there on the right does that. But I'm going to skip this one for now. That's probably enough to get you through this. All right. So question number 2. All right, a 1,500 kilogram car accelerates from this speed to this speed in 5 seconds. Calculate average power. So remember that power, how it's defined, it's the rate that energy changes, or it's also rate that work is done, either one. It can be calculated by taking your change in energy over your change in time, or by taking the work done and dividing by the change in time, either one. Now, where you're going to get this from, right? You've got a mass and 2 speeds here. You can calculate a change in energy, or a kinetic energy for each of those speeds, and then from the 2 kinetic energies, you should be able to calculate this. Or another way to do it, if you write out the work-energy theorem, which I'm doing now. This is supposed to be a W here, a work term. So a car on level road, there are no changes in potential energy. So we can just throw these out, basically. And then if we calculated a KE1 and a KE2, and we put the KE1 on the right, we'd have the work equals some number. And again, that's the same thing as doing this. So that should get you by number 2. Number 3. So 3 is another energy type of problem. I love energy problems. Whoops. So start with a good picture. Right? Here's the ground. Here's the arrow. It gets fired up at some speed. Now we don't know this, so we give it a name like V sub O or V initial or something like that. And this is what I would call position 1. Position 2, the arrow is at its highest point. And a key thing to realize is at the highest point, the velocity in position 2 would be approximately 0. So write out a work energy theorem for this. You got your PE1 plus your KE1 plus your work from 1 to 2 equals PE2 plus KE2. And there'll be no PE1, right? But you will have a KE1, and that'll be 1/2 m V squared. And I'll talk about work term in a minute. Your PE2, that's going to be an MGH term, and your KE2 is going to be approximately 0 because at position 2 the arrow's not moving much. Now the work term, like most of the problems I give you, is 0 because as the arrow moves through the air, if you picture what forces are acting on it, right? There's the gravitational force. The arrow has a certain weight, and that's pretty well it if we throw out air drag. So the gravitational force does work, but that's what the potential energy is taking into account for you. Basically, that term is here. So that should get you through that problem. Okay, number 4. An elevator is lifted by an electric motor in 10 seconds, right? So the change in potential energy of the elevator, the old saying, a picture is worth 1,000 words. I like to say in physics, it's 2,000. Okay, so here's maybe a picture, and I would probably label like the positions. Here's the elevator at position 1. It hasn't gone anywhere. Where? Here it is at position 2. It has been lifted now 30 meters. So to calculate the change in potential energy, remember potential energy is this quantity that allows you to decide where the 0 is. So if you put the datum here, your PE1 would be 0. Then you can calculate a PE2, which is effectively the change in potential energy. All right, part B, calculate the power in watts. So remember, power is change in energy over change in time. You're going to get the change in energy from part A. And then the change in time is given in the problem. And then part C is a unit conversion. Let's see. Question 5, a rock dropped off a bridge. Find the final speed after 3 seconds. So here's an example where a velocity graph would come in handy. So the rock is dropped. So if we were graphing velocity against time, right, the initial velocity, if we start timing it, the instant it's dropped would be something like this, 0, 0. Meaning at t equals 0, no substantial velocity yet. Then 3 seconds later, there is some sort of v final. So this distance on the graph, we don't know what that is. So you give it a name like v final and move on. And then we will assume constant acceleration. And this is a gravitational acceleration problem, right? So you have to ask yourself, what is the slope of that line? I'll go ahead and help you out with it. So gravitational acceleration, remember, has a value of 9.8 meter per second per second. You're going to use this to write an equation for the v final and relating it to the time. And that should be enough to get you through that. So this is just you can use like velocity as distance, or actually I'll say speed as distance over time. I'll just put d over t. There's almost nothing to that one. All right, so these are stuff you either know or you don't know. So if you don't remember the units, just remember, at least be able to know how they're calculated. You can always take units at face value. Here's what I mean. Work is force times distance. And hopefully we remember that force is a Newton times distance, which is in meters. So Newton meter, perfectly acceptable answer to that. You can also get units for the kinetic energy like this, 1/2 mv squared, and ask yourself, what is m and what is v measured in, and so forth. That should get you by these things. Okay. Use the position graph below to answer the following questions. Let's see, velocity. These are velocity questions. So this is a position graph, right? And remember, what's called your average velocity, that's what the bar means, is a change in x over a change in time. And hopefully we remember what that, from algebra class, that this is a slope. Remember from algebra class, change in y over change in x. Whoops, I'm sorry about that. My phone there started yelling at me, but that's an example of what we call slope. So I'm just going to make one up here. If we wanted to know the average velocity between, say, 2 and 10 seconds, 2 is here, 10 we're here, that would be the slope of this line. It doesn't matter, that's not actually part of the curve. And then we would take this y value minus this one over the times of 10 minus 2. That's how you work the rest of this problem. You answer the questions that are stated here. All right, so this is a velocity graph. A little reminder of what this means. Right, these velocities are all positive. That means this object is moving in whatever we're going to call the positive direction. Now, these velocities are decreasing. Don't mistake that for going backwards. Like, this thing is still moving forward in whatever direction we're calling positive. But the velocity is decreasing to this point. Now, the velocity is increasing in this region and constant. So it's kind of important to understand what this graph is, what this graph is telling us. All right, now, let's see. Question A, what is the velocity at 2 seconds? Oops, sorry, wrong graph. When is the particle at rest? So you're looking for a time, or ask yourself, is there a time where the particle's at rest? The velocity would have to be 0. So I'm not going to give you the answer to that right now. I'll let you think about that. But you're looking for somewhere on this graph where the velocity is 0. If you think there's no time, just put no time where that occurs. Okay, part B, what is the acceleration at 2 seconds? So at 2 seconds, we're here on what they call B. And you have to just know how acceleration is calculated. Right? It's equal to a change in velocity over a change in time. And again, remember from algebra class, change in y over change in x, this is a slope. And that's what this is, slope of velocity over time. So effectively what we're asking for here is the slope of this line. And I'll let you finish that. Okay, part C where it says at what time is the acceleration is 0. Again, acceleration is slope. So I'll let you look at the graph and you have to decide where is the velocity not changing or where is the slope 0. D, how far did it go from 3 to 5 seconds? So hopefully we remember how to do this. This is a velocity graph. And the area bound gives you the displacements. So for example, if you could calculate this area right here, that would give you the displacement between 0 and 1 second. Or 0 and 1 second. That should get you by this question. Okay, unit conversions here. So make sure you write them all out. For example, for this one, if you want to go from watts to horsepower, you have 1800 watts. You start with that. Then when you do unit conversions, you are always multiplying by a fraction. And I'm going to be watching for that fraction in your work. It's going to say show all work for full credit. And you have to know where to put the units. If we want to be left with horsepower and get rid of watts, we would need watts on the bottom, horsepower up top. Then we would look to our unit conversions here to know what numbers go where. Make sure you do not skip this step, because when I say show all work, that's what I'm talking about. And if that step's not there written out, you will lose points. Okay. So at the location shown, this bike is moving at 10 meters per second. Now, if the person starts kind of coasting up the hill, well, no, you know what's going to happen. They're going to kind of slow down and eventually stop. I'm just going to use a dot there to represent the bike. And this is a classic kinetic energy to potential energy situation. So you put a datum right through here. You write out the work energy theorem, your PE1 plus KE1 plus work equals PE2 plus KE2. This is your position 2, by the way. And again, because of where we put the datum, this would be 0. I'll go ahead and tell you, there's no external forces in this one, also a 0. The how high will show up in this PE2 term. And I'll let you think about the KE2. Keep in mind they're at their highest point. So ask yourself, are they still moving? Let's see. Oh, this looks like I missed a word there, but I'm sure that's supposed to read a car traveling 20 meters per second. A driver sees a deer and hits the brakes, stopping the car in 6 seconds. So without me doing it, to draw a velocity graph, ask yourself, like at t equals 0, how fast is the car moving, all right? Hint there, okay. And then 6 seconds later, it says the car is stopped. So 1, 2, 3, 4, 5, 6. Think about it. The car is stopped. Where would we put a dot on that graph? Then you make your standard constant acceleration assumption. Connect those dots by a line and start answering the questions. Now remember that how far. You calculate displacements or change in x's by velocity times time. Remember, on a velocity graph, that's like this dimension and the times this dimension, and the product of the two is area. So whenever, when you get this graph sketch, it's not going to look quite like that, but then this area here will tell you the distance traveled. Okay, the next part where it says calculate the acceleration. So once you have your graph, slope is the acceleration, because acceleration is change in velocity over change in time. And I do expect you to know formulas like this for your test. Oops, trying to look for oh, there we go, the scroll bar here. Well, that's pretty well it. So that's your midterm exam, what it's going to look like, and expectations here. I do expect that you know how all of these are defined up top: velocity, energy, potential energy, power, acceleration, kinetic energy. Without having to look them up. I do expect simple formulas here. So for example, like gravitational potential energy is mgh, kinetic energy is 1/2 mv squared. These I expect you to know without having to look them up with notes. Velocity is delta x over delta t. I expect you to know that. Power is change in energy over change in time. I expect you to know that. No notes. Okay. I expect you to know the work energy theorem, PE1 plus KE1 plus. You've seen me write it lots of times. Okay. And these problems all would be, you know, assuming no notes. All right, and you're also not allowed to bring your own calculator. You have to bring somebody else's calculator here. So, or they will give you one at the testing center. So that's pretty well, in a nutshell, all things you're going to be expected to know. You notice it's kind of high in work energy methods. Well, that's important. I think that's probably your next one's going to be high in work energy as well, because energy is such an important concept in physics. It goes a long ways towards understanding the universe. So anyway, if you have any trouble or can't get these answers to work out on this, give me a ring. Hope you have a great weekend. Have a great day.